Hello, everyone. We are starting our last lecture. Our last lecture will be about weighted colimits and Tensor-Hom-Cotensor situations. These are two topics that happen to be the last ones that I wanted from the beginning to be central. And Professor Marcinkovsky also asked me to make them somewhere in the middle that I can use and show how they appear more in the course. However, we needed so much preparations and material as scan extensions, pro-functors, enriched category theory, that it took us so long up to the end when I can finally determine what is what and who are our main heroes. So I want to start today first part. It is about weighted co-limits. Maybe you maybe you ask yourself, why did I give one of the alternative definitions of a limit in a rather specific and strange way when we had lecture about limits and colimits? What I'm talking about right now, I'm talking about the definition that used our legs of limit and colimit, so this slope sides coming out of the tip of the cone to the bottom, and I do not took them all at once, but I was taking them separately, and I was saying that the definition will be used later. Here, what do I precisely at our leftmost column? What do I mean? So if we have functor G going from category J to category C, and I want to take limit of this functor, I am considering the following two cell filling the picture. So I'm taking a terminal functor going from category J to trivial category to unique functor, and then embedding category with one object in a category of sets. It's just picking up a singleton. This functor I wrote with red, and it is functor that I call one terminal functor. So my natural transformations from a terminal functor to the following composition of functor G and representable functor will correspond precisely to the legs of the cone. So the functor, the set of legs, is representable by certain object that is called limb G. Then we call this limb G being a limit of our functor G. So what do I mean? That if I want to spread legs from object C, it is the same if I will spread legs from object limb G, and I will join C and limb G with a single arrow. So this is precisely the factorization of a bigger cone with a tip C through the cone or with tip limit of G. Then in this construction, we have one thing that is pointed with red. It is terminal functor one. So this is a terminal functor, which is a composition of two functors, one going to the terminal category and one from the terminal category. And we have the following question. What will happen if category of sets will be replaced by some Cosmos V? So in Cosmos, when we have Cosmos V and enriched category theory, we do not have such terminal functor, as we don't know how to choose. Right now, I'm looking at a central column, how to choose and what is a functor from any category to a trivial category. This is not clear, and we cannot be so sure how to do this, and there is no unique way. Even the functor from terminal category to any category can be chosen and fixed. So we need some solution to this thing, and the solution is very simple. If we cannot pick up terminal functor one, let's just pick up any functor. Maybe sometimes in certain settings it will happen to be terminal functor one. Maybe it can happen to be some other functor, but let's see what will happen. So we are changing our functor 1 by some functor that we will call weight. It is going from our category G to self-enriched category V, which is sending every object to its certain value. For colimits, we have similar situation in a third column. I wrote f opposite for our functor f because I want to compose f with a contravariant representable functor c blank c, and to do this I need to land in category C opposite, and if I am given functor f from category J to category C, I'm taking opposite. So the picture is exactly the same as before, but we are using contravariant functor blank comma C. Again, we are going to replace terminal functor 1 with a certain weight. Right now, I only wanted to emphasize that in the first case, terminal functor 1 was going from category J. Here it's going from category J opposite. So we will be replacing with two different weights. One weight will be covariant and one will be contravariant. So covariant for limits and contravariant for colimits. A little later, we will also read of this obstacle too. So what do I mean by weighted limit of functor G by weight W? By this I mean object that represents the functor which is given by the set of all natural transformations from our weight W, so replacement of terminal functor, to our cone with a tip C going to the image of functor G. So if such object exists, then we will call it weighted limit of G by the weight W. Here is a picture of where our functor G and W are going. Okay, for colimit, I have a similar picture, but I'm taking weight U and taking natural transformations to co-cones, starting from image of functor F and going to cotip C. If such functor can be represented by a certain object, which is called colimit of F weighted by functor U, then we call this object weighted colimit of F by U. In the middle, you can see this picture, which tells us that I'm replacing a tip of cone, so it's a single object, with some image of category of indices where we are starting. So this becomes a cylinder. So our tip becomes not one object, but a bunch of objects and arrows between them. And when we are trying to factor, we'll be factoring cylinders through other cylinders. That's what we are doing. Well, you can also remark yourself that my definition that I gave is given in a set theory, in a setting of Cosmos set, but it can be equivalently given in any enriched setting, where we will replace set with arbitrary Cosmos V, and all our factors and natural transformations are going to be enriched. So this was a remark in the third column. Well, I won't be myself if I will not provide you any formulas how to compute the things using ends and quants. As you remember, our main tool is a quant calculus. So weighted limit and colimit can be easily computed as the following end and quant respectively. However, the only one obstacle is the following. When we are will be computing the things, that value of our weight belongs to category V. And here for our weight, value of our weight belongs to category V. Values where functor G takes place belong to category C. And here f of A also takes values in category C. For this reason, we need to know how to take cotensoring operation between objects of V and category C. So for this reason, we need C to be V cotensor. Before, in the previous or pre-previous lecture, I gave you the notion what is tensor to cotensor. And I will give you again a little later today, when we will be talking about Tensor-Hom-Cotensor situations. But for brief reminder, I will tell you that cotensor is so cotensoring with object C is right contravariantly adjoint to a contravariant Hom functor. So this is right contravariant adjoint to contravariant Hom. Tensor, I don't think that you will be surprised, tensor is left covariantly adjoint to covariant Hom. So if such a thing exists, then we can talk about weighted computational formulas for weighted limits and columns. Or in the other way, oh, 1 second. Okay, Rahul left. Well, no problem. Everything is recorded and will be posted. So if such integrals exist, they will precisely define limit and colimit. However, if our category C is not tensor to cotensor, still they can exist because the formula in their definition is valid for any category, not when it is tensor to cotensor. But if it is so, then we can find such ways, such solutions. Okay, then are there any questions up to now? Okay, if there are no questions, then I will proceed. We'll have examples, don't worry. We'll have a lot of examples. No, here we'll have a few examples, but later we'll have a lot more. Okay, then if we will use and work around these formulas more and use an alternative way of computation and coend, we can recall how it was defined using category of elements, and we obtain formulas in the left column on the screen. So first one is a formula of weighted limit using category of elements. So we are taking category of elements, we are applying domain functor. So every point in what's category of elements, pretty much you can think of category of pointed objects. So every object has a certain point in it. And we are taking the object, the set where this point is picked up, or index of this set, basically, and then applying functor G and taking limit of that. And this formula works when C is complete. This, if C is complete, then we have this cotensoring property, and also limits exist and so on. So when C is complete, we can compute this way. If C is co-complete, we can compute co-limits also in the mentioned way. You will can also ask me, why did I put here category of elements, here such comma category? Well, opposite of category of elements of contravariant functor U will be precisely this one. So there is nothing to worry about. It's basically category of elements or of contravariant functor can be easily written as a comma category. If it's covariant functor, it's better to leave it as a category of elements. However, it's still, if you will look earlier in lectures, can be written as comma category. Now let's look at a few properties of weighted limits and colimits. There are much more of them, but I won't be talking right now about them all. So first one is that if our weight and functor are parallel to each other, so our functor takes values also in category of sets. I'm talking right now about ordinary functors, not enriched ones. Then our limit of functor G with a weight W is isomorphic to the set of natural transformations from weight to our functor G, which we are taking. Why and how did it happen? Just use our coend formula. And from coend calculus, we know that set of natural transformations can be given by the end, and that end will be precisely the end that appears in formula for weighted limit. Okay, for second property is the following. If we will weight our functor g with a representable functor, so our weight is representable, this will give us evaluation on a representation object. How does this appear? Well, this is our unit dilemma. If we will use contravariant weight and use and for any functor f, then we will see, again, application of contravariant weight as a weight for colimit will give us value of a function on that representing object. It's co-unit dilemma. So here again, matter what is a weight. So if we do not have a representable weight, situation can be worse. But still, it can give us some nice examples picking up not arbitrary weight, but specific one. So for the best and the most frequently appearing cases, we have statements of UNEDA and co-UNEDA dilemma available, and we can immediately compute it. When we are weighting by actual profunctor, B sub k. You asked me how to weight with a profunctor. Just wait till a few minutes. We'll find right can extension of functor t. Here is a picture along functor k. If we are weighting with another, now co-representable profunctor, then we will have left can extension. These formulas can be rewritten in the following way: that B sub k cotensor t is isomorphic to ran k t, and B super k t tensoring. I'm putting tensoring with the profunctors on the other side, will be len k t. Also, this formulas and allows you to do a lot of calculus with using profunctors and coend calculus. So to derive how to take repeated can extensions and so on and so forth. So our can extensions, we can say also, are partial, can be also defined using weighted limits and colimits. Property number 4, it's about end and coend. So we have end and coend that can be also computed using Hom profunctor, but now this Hom profunctor is considered as a functor of a single variable, the single variable being two variables. So if you consider two variables as one, then we can consider this functor as contravariant and the same one as a covariant. Since it has C op and C, we can jungle them how many times we want. All the weights are isomorphic, and we can pick up weight for limit and weight for colimit. So taking weight for limit, we'll get end, and taking weight for colimit, we'll get coend. Functor t is being arbitrary. So our ends and coends are also defined by limits and colimits. Before you saw that limit and colimit can be given by ends and coends. So here we have a loop that weighted limits, colimits define ends and coends, and ends and coends, if they exist, will define limit and colimit. That's such a little strange, but also a natural thing that we have the same phenomena, but we'll look at different from a different perspectives on the same thing. So I want to summarize that set of natural transformations, unit dilemma, co-unit dilemma, end and co-end, right can extension, left can extension, can be all computed by limits. As people sometimes say, where are your examples? Because I'm talking about some abstract theory, but also I should sometimes talk about examples, I will say that my theorems are my examples. So applications of the notions that I am giving, if they are generalization of certain well-known notions, then these well-known notions are my examples. So right-hand extensions, left, ends, coends, evaluations of different functors, natural transformations are precisely examples of ends and coends. But we will see more concrete some results a little later. Okay, right now we were weighting functors with a covariant and contravariant weights for case of limits and co-limits respectively. From this point, I want to jump a little further and first of all reveal some hidden machinery, and second of all, I want to rid of this inconvenient thing when we need to talk for limits about covariant functors and for colimits contravariant functors. We can talk about profunctors and weight being profunctor, and don't think about its covariant or contravariant. Here is what do I mean. So if I am picking up profunctor P, which is going from category A to category B, I will remind that it's a bifunctor from A of tensor B to category V, cosmos V. If I'm picking up such profunctor, it will generalize both weight for limit and for colimit respectively. So once I have such functor and have a functor in the first case G from category B to category C, I will write down the same formula as you see right now, the first black formula in the left column. I will write this formula for limit, weighted limit, where weight is a value of a profunctor when object A from category A is put inside it. So our profunctor becomes a functor from category B to category V, because A is already substituted in the formula. So when I will write such thing, I will have a weight parameterized by objects of category A. Therefore, the limit that will be obtained also will be parameterized by objects of category A. So it becomes, the limit should be object of category C, as we know from the definition of weighted limit and co-limit. But since it's parameterized by objects of category A, and it can be checked that this thing is functorial, we will see that limit of a functor weighted by a profunctor becomes a functor from category A to category C. Here is precisely the picture to the below the upper triangle, where I just wrote not equal. All these triangles are not necessarily commutative. It's just three functors given by a diagram. Similar situation holds for colimits. I am writing down the definition of weighted colimit, and I have my weight being a profunctor where one object, where the covariant argument is fixed, and there we put object B. Then my representing object, colimit of functor f weighted by profunctor P, will be also parameterized by objects B, and also it should belong to category C. But it has parameters B, values in C, so it becomes functor from B to C, and we have the last triangle in the left column. Also, for the reasons that will be obvious a little later, and I was using also this notation in coends, I will write limit of functor G with functor P using cotensor operation, because we can act with the profunctors on functors on the left using cotensor or ends. When we are talking about colimits, then I can use tensoring of functors by profunctors and this is a write action, so I can write it on a write of it, using again tensor notation. The reasons for this will be clear in a half hour or even less. So that's all what we need to define value. What is a weighted weighted limit or co-limit of a functor by a profunctor. From now, we don't need to worry and think of whether is our weight covariant or contravariant. Also, if we will take a look again at these formulas, formula 1 with 1 dot and formula with 2 dots on the left column, and we will clear all the letters A, C, B, and so on, we will have the following things. So on a site where we have our weight, for instance, on this side, left-hand side in the formula number 1, we have precisely value of a right can extension of one profunctor by another. Here it is on the right. So it is a right can extension of co-representable profunctor by another profunctor. But this thing also appears to be connected with weighted colimit in the following way, that such right can extension of one profunctor by another is co-represented, and co-representing functor is colimit. So from this, I would immediately say that if we take if weighted limits and colimits exist, and for them to exist, we need certain limits, sorry, not limits, our category to be tensor and cotensor, category C. So then taking a right can extension of co-representable functor will end up with a right can extension with, again, co-representative profunctor. And co-representing objects will be colimit. Before also the last lecture, I said, and I used the following notation, so that co-representable profunctor right divided by P will be isomorphic to the of F tensor P. The second formula for weighted limit tells us the same, that right can lifting of a representative functor is again representative, and the representation functor is a limit. So here we have left division by P, and here we have this thing. Again, I gave computational formulas just to remind everything what we had before. So limits will give us the result of taking limit will be that we'll change the domain of a functor G. So we have functor G starting from B landing in C. We will change domain from B to A. And when we are talking about colimits, then we are changing the domain of a functor, codomain. So, oh no, 1 second. Oh no, okay. We are again changing the domain of a functor, but in a different way. So in one way covariantly, in one contravariantly. Contravariantly for limits and covariantly for colimits. Well, right now, I will explain why did I do all this, not just for my own convenience, but also for the purpose to write down the adjunction formulas. Before we had very simple and easy observation that limit, as we had before, was right adjoint to a constant functor. And constant functor was right adjoint to colimit. This was before. Right now, we want to find appropriate generalization of this fact. So whether weighted limits and colimits have adjoints, and if they have, how does this adjoint look? Because there are no constant functors in our enriched setting. Again, we are starting from a profunctor P, two functors f and g, and we are writing two formulas. How can we obtain them? We can obtain them from the above definition, just changing the object C by value of certain functor, and then using the fact that the things are getting natural in all variables. So we can derive from a definition of weighted limits and colimits these formulas. And here it appears that colimit of profunctor f weighted by colimit of f weighted by profunctor p appears to be on the left, limit appears to be on the right, but something also appears in between of them. This is profunctor twisted Hom in category C, but it's twisted in both variables, first one and second one. So first variable comes from category A, and second variable comes from category B. From such triple adjunction, where I called first formula 1, second 2, third 3, I can derive 3 adjunctions. This will be the core of the second half of my lecture, and this will be called Tensor-Hom-Cotensor situation. So we have 3 adjunctions at one spot, 2 covariant, 1 contravariant. From formula 1 and 3, we derive that colimit and limit are adjoint to each other. Well, this was the same for limit and colimit. However, when we will be talking about adjunction to functor delta, to constants, we won't have it. We'll have something similar. I was not writing down all these special cases and formulas, but as for now, I wanted to emphasize that from this triple adjunction, we can derive 2 more formulas. So tensoring profunctors with functors, this operation is adjoint to the following twisting of Hom. And conversely, cotensoring is right contravariantly adjoint to another twisting of Hom. As you see here, I put blanks in C, but these blanks will take the not argument in category C, but functor, which ends or which has its codomain in category C. So here we'll go functor G in this spot, and here in this spot we'll go functor F. So from formulas 1, 2, and 3, we derive 3 adjunctions, 2 covariant and 1 contravariant. This is quite a beautiful thing, as we will see very soon. But right now, to finish story about weighted limits and colimits, I wanted to give you 4 examples. Well, first example will be that if we have our colimit weighted by the terminal functor, in case of V equals set, and terminal functor, as you remember, it takes every object J to a singleton, then we obtain ordinary limits and colimits. Please don't mix up lim1, colim1 with derived limits and colimits from algebraic topology and so on. Such things also exist in categories, but that's a different. I mean here weighted limit and weighted colimit by terminal function. So our regular limits and colimits are special cases. Kelly and MacLean as I remember, call them conical limits and colimits. So conical, the ones that have the base of cylinder from where we start as a single point. So usual things, but when we are talking about general weighted limits and colimits, we need basically to talk about cylindrical limits and colimits. So conical not always exist, and if they exist, uh, they are partial cases of cylindric ones. Okay, second property is that category of elements also can be defined as weighted colimit. But here it's very funny weight. Who is the weight here? The weight here is a functor that takes object of a certain category to its comma category. So we have fixed category C, and for any functor C, we are giving comma category. So all the category of all morphisms going out of this object, and this will be a weight. As you see here, our cosmos is a category of small categories. So our weight will be a category valued functor. Number 3 is so-called comma object. So suppose C is a 2 category. I will recall that 2 category is a category whose sets of natural transformations are not just merely sets, but their categories themselves. So they are the objects, there are functors, and between them are natural transformations, and we have horizontal and vertical composition. So if I will take functor G from a 2 category, very trivial one, having just 3 objects, 0, 1, and 2, and making such cospen, then it's picking up some diagram in C. This diagram will be with 3 objects, B, C, X, and 2 arrows, F and G. And if our weight will be embedding of 0 and 1 inside the interval, so here's an interval category, so from 0 to 1, category is just 2 objects. 0 is category just with 1 object. So 1, pardon, here should be from 0 to 0. It's embedding 0 to 0. Here is embedding 0 to 1. So embedding in the bottom and embedding in the top. And if we will take such weight, then we will obtain comma object of F and G in category C. So what is comma object? I decided to also write down it. It is terminal cell among all such cells, as you see here. So we had cospan. This cospan we are closing with a certain object on the top left and filling this diagram with a natural transformation. And among such fillers, we can make order who is dividing whom. And the terminal cell, if it exists, is called comma object. When you will take instead of category C, not any 2 category, but category of small categories, your F and G, this morphisms, will become precisely functors F and G between categories, and your comma object will be precisely comma category in a category of all small categories. So this is the thing that you use to work. And it will be terminal in the same sense as I said. So comma categories, or more general comma objects, are instances of weighted limits, of weighted limits. Number 4, I decided to pick up a very algebraic example. So I have a, if I will take category R, or this is a category, this is an associative ring with identity. Sorry, that's just a ring, and category I'm taking to be V, chain complexes of R modules. Then for any chain map of complexes, F small from X to Y, I can find a way to pick it up from category of all chain complexes. It's with a functor F capital. So V1 here on this side is an enriched interval. So we are taking interval category. So it has two objects and one non-trivial arrow and enriching it in category of chain complexes. I don't want to talk much about this, but it's not difficult to do. Then we are taking a functor from this category, and this functor to go into any category will be picking there in the target precisely one morphism. Similarly, what we do in just general in ordinary category theory. When we are taking contravariant functor, our weight u, we want to pick up something special, and the special will be a chain map. Here I have a complex. It is degree 0. It is degree 1. I have two chain complexes and chain map between them. Here is my unit disk. Here is my identity. It's embedded in a unit disk, things that this complex represents. And I have always such chain map. Then when I'm taking colimit of functor f with respect to weight u, I need to take, I will compute it using quant. My quant, since my starting category is very small, it has just one non-trivial morphism, will give me such diagram that I'm writing down now. So will give me only such diagram, and then of this diagram I need to take, in this case, push out, taking colimit, and in this case it will be push out. So push out of this diagram will, if one compute, will be precisely cone of chain map. So cone of chain map appears to be a colimit of one functor weighted by another. I want also to emphasize that everything is here enriched. You cannot pick up something from ordinary category, map it to the enriched category. I mean, you can in general, but will it work? I won't guarantee. So all your setting need to be homogeneous in a way that if all functors are ordinary, then they're all ordinary. Your category is ordinary, all functors ordinary, and so on. You can take ordinary categories and additive functors, or additive categories and just functors between them. Then think, why do you need this additivity on categories? Okay, so here what I had for weighted limits and colimits. Are there any questions? Okay, if I see that you are shaking your head. Yes, Sean, I see everything. And well, you can ask me some mathematical object, you know, that I haven't mentioned. Think about it for a second and ask me, will it be weighted limit or colimit? Just pick up any. Yeah. Just don't be shy. We have a few minutes, a few minute break just for me to take a deep breath. Think about some object categorically that is made, and then we'll define, is it weighted limit or colimit? You can open any book if you want. For instance, a cylinder of map in algebraic topology or in homological algebra. It's also a chain. It's also a colimit weighted one. Just you need to think what will be the weight. So the weight will be a little different. So you will have one arrow here, an additional arrow here, and here will be something else. Okay. When you will be looking for mapping space or for mapping cone, not mapping cone, from path space and fixed path space, you'll be taking other diagrams like this and taking here weighted limit. So all these algebraic geometry things are already well written and are defined in this thing. If you think about double mapping cylinder, so if you have a cylinder, but your bottom and the top are curly ones, so you are attaching the image of certain other space. It's called double mapping cylinder, so it's just good in the middle, but we are gluing something to the top and to the bottom. This also can be given by this guy. This is also a weighted colimit. What else I can think about right now? This was the most obvious thing. Everything that can be defined universally at certain point is defined by limits, colimits, and to a certain extent by can extensions. But can extensions, as MacLean thought that they are on the top, but on the top of them are weighted limits and colimits, because can extensions can be defined using weighted limits and colimits. So if everything or almost everything which is universal and good is can extension, so everything is weighted limit and colimit. That's why my question, if you were not silent but answered me, just picked up any object, will always have a certain solution. It doesn't matter what I would say, I could be wrong, but if you will take more time and explore the situation, you'll find that you can't escape them. They're everywhere. Just matters who is your weight and who is your function. Okay. Now we will go, since there are no questions, to next topic, which is Tensor-Hom-Cotensor situation. To talk about Tensor-Hom-Cotensors, I want first to talk about one example that's well known for everyone. It's about Hom tensor adjunction. So what do we have? If we have two modules, I picked up left modules A and B over associative ring lambda with unit, and I will take a abelian group S. Then I can always form tensor product of abelian group with a module, because module is also an abelian group. Left lambda module structure is preserved on module A, so still the objects that I will obtain will be a left module. Between left module S tensor A over Z and module B, I can take a abelian group of all lambda homomorphisms. From Algebra 2 or any similar course, I know that tensoring operation, tensor product of modules, has right adjoint and its home. So we can move either home of we can move with the home either S, either A. So I obtain two isomorphisms, but together we will have three formulas and three isomorphisms between them. And these formulas determine two adjunctions, at least two, actually three. I just skipped the third one. First one is usual tensor Hom adjunction, and second one is an adjunction that contravariant Hom is self-adjoint. Today I already said that if contravariant Hom has right contravariant adjoint, it's called cotensor. So cotensoring in this case will be Hom over Z. Tensoring will be tensoring over Z. And our Hom that we took was in category of left lambda modulus. So from this example where we have two adjoints, we have contravariant, actually two contravariant adjunctions and one contravariant. We see that it works to think about the situation, such situation in the most general way. It was defined in one of the articles of John Gray, so-called Tensor-Hom-Cotensor situation or triple adjunction, or many people call this thing differently. What is it? It is a sextuple of three categories, S, A, and B, and three bifunctors, tensor, Hom, and cotensor respectively, where tensor is what operation? It's an operation that takes category A and acts with category S on it covariantly. You can think about this as a multiplication. And the results are in category B. You have operation that's called cotensoring. You're acting on category B with category S, but contravariant. You division. And the results are in category A. And also we have a certain thing that pairs together objects A from category A and objects from category B. And this is the result will be in category S. Category S can be thought as category of coefficients, category of something that is acting on both A and B, covariantly on A and contravariantly on B. But still it should be connected to their internal pairing. These bifunctors should satisfy the following adjunction. So our S tensor A mapped to B can be transformed into set of, not set, object of all morphisms from S to internal Hom from A to B, or in objects of morphisms from A to S cotensor B. So I will add to it that our blank tensor A is going from S and is adjoined to a Hom where contravariant variable is fixed. Also, we have another adjunction. Another adjunction is the following. If you will take S and tensoring blank, we are going from category A and we will land in category B. And this is given by cotensor. So here I'm taking third and first formula. And the last one is the following. If I will fix B, so here I will have Hom blank comma B, and on other side I will have blank cotensor B. Both functors are contravariant, so I'm just without ops writing contravariant adjunction from A to S. So here are two covariant adjunction and one contravariant, and they're all joined by this triple isomorphism. The example to the left tells us the case where one of the obvious cases when we have it. The other obvious case is when we have symmetric closed monoidal category V, and our this means that our tensoring operation on category V has right adjoint given by so-called internal Hom. Since our category is symmetric, we can jungle here S and X in this formula and write two isomorphisms using this adjunction above. Then comparing this formula to the definition of Tensor-Hom-Cotensor situation, we derive that we have a Tensor-Hom-Cotensor situation where coefficients are V, categories that we are pairing together are also V, so self-enriched category. Tensoring is given by monoidal operation on category V. Then Hom is given just by Hom profunctor, and cotensoring is also given by Hom profunctor. That's it. So we have Tensor-Hom-Cotensor situation given for free in a case when V is closed symmetric monoidal category. The other example, is the one that we had already today, is so-called cotensored and tensored and cotensored categories. Now I will remind it again that category C is V tensored if covariant Hom has left adjoint, and this left adjoint is given by tensor by functor, and we have the following adjunction. Category C is cotensored if contravariant Hom has right contravariant adjoint. So we have a bifunctor cotensoring such that the following isomorphism holds. Category C is called V bitensored. That's my notion. Usually people write that it is tensored and cotensored, but it's a little too long. So as in case of complete and co-complete categories, I will just use bicomplete thing, and instead of complete, I use adjective tensor. So C is bitensored category if it's both tensored and cotensored. This means that I have triple adjunction here. So being tensored cotensored, it is nothing else that we have a pairing with the of a category with itself. Coefficients are our are from Cosmos V. Then tensor operation is a tensoring bifunctor, cotensor operation is a cotensoring bifunctor, and our Hom is given just by Hom profunctor on category C. So our category is bitensored if and only if the thing that I'm right now underlining with a red is Tensor-Hom-Cotensor situation. So to say that this is Tensor-Hom-Cotensor is literally means to say that it is bitensor. Here is an example. I think I gave this example already once, but I decided to give it again. Now, in light of everything that I said, it should be more illuminating. So if A is a category with all coproducts, A is a regular category, just not enriched one, then we have the following adjunction. Adjunction from coproduct of object A S times to object A prime. It is the same as set of S arrows indexed by set S between A and A prime. It is the same as arrows from object A to product of object A prime S times. This thing can be very easily shown. So first one is, I would say, picture represents this thing. Here is A prime, here is A. Second picture represents a few arrows from A to A prime, and the third represents from one object A to bunch of A primes. That's it. So the triple isomorphism above, it's pretty much tautology. Then we have the following Tensor-Hom-Cotensor situation, where tensor is given by copower. By copower, I mean taking disjoint union so many times as we need. By power, I mean cotensoring. sorry, by cotensor I mean power, so taking some object product with itself so many times as we have objects in the set S, and we have Tensor-Hom-Cotensor situation. Okay, the other example comes to us immediately. If our category D, right now I picked up category D, is V by tensor, then, as we established just before in the remark, we have Tensor-Hom-Cotensor situation given by tensoring and cotensoring and Hom perfunctor. After this, I am taking any category C, and I am considering all functors, category of all functors from C to D. Then, since my D is bitensored, I can redefine tensoring and cotensoring on functor category pointwise. That's it. So if our target is bitensored, then functors, so functors valued in a bitensored category are again bitensored. And bitensoring is being pointwise. Okay, this is a very good way to say it. So if I have a pair functor and coefficient from V, then I will bring them together and I will have F blank, tensor, and V. So here this blank waits for object of C. Once it gets object of C, it will be object of D. And with object of D, I know how to tensor because D is tensor. So I am getting well-defined functor from C to D. Similarly for cotensor. But just now cotensor sign. What will be in the middle? Before in the middle was Hom from one object in D to another one. Right now it will be natural transformation from F to G. So internal Hom in this category. That it is Tensor-Hom-Cotensor situation, and now our category is V by tensor. To see this, you can use quant calculus, all these yoga rules of how to move ends and coends from inside outside, use usual adjunctions from D, because D is V by tensor. And you can prove that it will be, this functor category will be V by tensor. So tensoring or cotensoring is inherited from a target category. The next group of examples, oh no, before next group of examples, I will have something very small and quite obvious. So it's a corollary. In this corollary, I am joining two facts from above. First one is that what I just said, if D is V by tensor, then any functor category from C to D is so, and taking D to be category self-enriched category V, which is always by tensor, picking up any category C, I obtain that functors from C to V form V by tensor category, and contravariant functors from C to V also form V by tensor categories. So category of here copressheaves and category of pressheaves are always V by tensor. Co/pressheaves are always by tensor. Not only tensor contensor, but by tensor. Okay, since we were talking today about weighted limits and colimits, it's very natural to recall the picture that we had before, not necessary commuting triangle with a profunctor and two functors. And then we can define Tensor-Hom-Cotensor situation where our tensoring will be given by colimit, cotensoring by limit, and twisted Hom will be our Hom for Tensor-Hom-Cotensor situation. The adjunction formula we already had today. In this adjunction formula, we immediately identify our heroes, and just comparing it with a notion, with a definition of Tensor-Hom-Cotensor, we identify who is our coefficient. So our coefficients are profactors. So it's our V, sorry, not V. It's our S, category S. Here, okay. Never mind. It's a bad choice because I have already A and B. I can't write F, A, and B because I already have A and B. So profunctors are coefficients, and we are pairing together functors with the same target, category B and C. So these are limits and colimits respectively. I want here also to emphasize that all this is true when C is V by tensor. If C is not V by tensor, I won't be able to write my limits and colimits in a way of ends and quants, so I won't be able to prove this triple adjunction. So my triple adjunction will exist if C is V by tensor. If your favorite cosmos is set, you are working just with set functors, or if your favorite cosmos is abelian groups, you are working with pre-additive categories, in particular additive, abelian, triangulated, and so on. Then you can always think that since category of sets is bicomplete, category of abelian groups is bicomplete, presheaves on them are bicomplete. If I am taking category C to be bicomplete, that everything will work. However, since I'm trying to talk as most general as possible, without giving anything specific, I am assuming that C should be V by tensor. Right now, if I will go back to this thing, and I will substitute here category C by category of presheaves, and why I can do this? Because I am since I am requiring category C to be V by tensor, I can substitute C by any well-known to me by tensor category. And we just have found that category of presheaves is by tensor. Okay. So I'm substituting C with C op to V with my presheaves and obtain Tensor-Hom-Cotensor for profunctors. Okay, also, how can I do this? If I will have A, so I had before category of functors from A to C. Right now I will have from A to C op, comma, V. This is isomorphic to A tensor C op, comma, V. It's just a junction for so function of two variables can be considered as one function with values of functions of another variable. Then swapping C and A from one side to another, I will get that C op tensor A, comma V. But this is precisely by definition is a profunctor category from C to A. Here it is. Very small exercise. So my functor category becomes profunctor category when I am picking up instead of C category of presheaves in C. And then doing similar thing with functors from B to presheaves, I obtain again the profunctors from C to B. So my triangle, this one, will be substituted by such triangle. And triangle of profunctors from previous lecture, I know that gives me Ran and Rift. So right can extension and right can lifting. Right can extension is a division on the right can lifting is division on the left. and composition is instead of product. So here I have triple adjunction from the last lecture. Then identifying the objects that I need for Tensor-Hom-Cotensor situation, I obtain that 1, 2, 3, 4, 5, 6 tuple, 3 categories and 3 bifunctors give me Tensor-Hom-Cotensor situation for profunctors. I hope I have what's called not insisted, convinced. I hope I have convinced you that Tensor-Hom-Cotensor situations are everywhere. So everything that we were doing up to now is given by Tensor-Hom-Cotensor. So pretty much always you have the third one. If you have a junction of one with something else, then you need to think a little more, and maybe you have the third adjoint, covariant to first and contravariant to second. Now, after this remark, I am taking the next step, and I am recalling that any associative ring with identity can be considered as one object, category, enriched in abelian groups. Multiplication becomes, in a ring, becomes composition, and additivity, addition in a ring, is going to be an enrichment of Hom set when it becomes an abelian group. So if I have 3 associative rings with identity, lambda, gamma, and sigma, then I can form Tensor-Hom-Cotensor situation. But here I use a rule that lambda modules are functors from lambda to abelian groups. Right gamma modules are contravariant functors from gamma to abelian groups, and bimodules from left lambda, right gamma are profunctors from gamma to lambda. So 1 and 2 implies 3. Then my bimodules here, you can think about the bimodule category from sigma to gamma, both sigma, gamma, lambda rings as left gamma, right sigma bimodules. Then another bimodule category, another bimodule category. So when you have these 3 bimodule categories and 3 bifunctors, tensoring over gamma, lambda Hom, and sigma Hom, then we obtain Tensor-Hom-Cotensor situation for bimodules. It just immediately follows from the Tensor-Hom-Cotensor situation for profunctors. So it's just a consequence. But you can prove it in a ring and module theory by hand. However, nothing very important is not going there. So everything is given by right-hand extension, right-hand lifting, and by composition of profunctors, by ends and coends. Yes, it's a little surprising, but right-hand extension, right-hand lifting here becomes Homs in category of lambda modules, left lambda modules, and right sigma modules. So it's just looks very hostile working with profunctors, but boiling down to well-known situation, it can become very friendly and tame. In particular, I decided to write again the example from the beginning that I gave you. If I am taking category of lambda modules, it's bitensored by abelian groups. And in this situation, my tensoring is given by tensoring over Z. Hom is as in Hom in lambda modules, and cotensor is the Hom in abelian groups. You can derive also this formula immediately from a case above, just thinking who is your lambda, gamma, and sigma, and picking up correct, so making a correct choice will give you immediately this Tensor-Hom-Cotensor situation. Okay. And the next step is CAN extensions. I picked up not all CAN extensions, but the specific ones. So for to have all CAN extensions, I need to land not in Cosmos self-enriched category V, but in a random category. I decided not to do this, just to do the thing that what I have right now. However, that thing is also possible, but using a little different setup. So why it's possible? Because it's because of weighted limits and co-limits. Weighted limits and co-limits give you Tensor-Hom-Cotensor situation, and there you can, picking up correct functor, you will have Tensor-Hom-Cotensor for len and ran. So if I have a picture left functor L from B to V, and it's going to be extended via functor H from B to C, and I have a random functor R from C to V, then the third and first formula are defining left CAN extensions, and the middle one comes from Tensor-Hom-Cotensor situation. But how to derive them all together and know who is first, who is second, who is third? Okay, who is first is pretty much obvious, right? Because left CAN extension standing on the left is tensor. But among these two guys, who is tensor and who is cotensor? Okay, to know this, we need to think a little deeper, that this picture that I just draw here can be made in a picture for functors. Using a co-representable embedding of small categories in profunctors, my functor from B to C, H, becomes a profunctor from B to C, C superscript H. And functors from B to V and from C to V, L and R, becomes functors, profunctors, excuse me, from trivial category to category B and category C. So we have again triangle of profunctors, and this triangle of profunctors precisely gives me this triple adjunction, because three profunctors that can be made in a triangle give me Tensor-Hom-Cotensor situation. I mean, I already have Tensor-Hom-Cotensor situation, but that adjunction formula for Tensor-Hom-Cotensor situation should be written for three functors that live precisely in a triangle. So I see that left CAN extension is a tensor operation, composition is a cotensor in this case, and twisted Hom, so Hom in category V twisted by functors L and R, is our Hom for Tensor-Hom-Cotensor. Similar situation for Ren. I'm starting with this picture, with such one. I'm turning it into triangle of profunctors. For triangle of profunctors, I am writing the adjunction. And in this adjunction, I am looking who is standing where. Since I have an agreement that first is going tensor, then Hom, then cotensor, I can easily identify who is who. So composition here becomes tensor, not as before cotensor. Cotensor is Ren, and twisted Hom is again Hom for this thing. So the moral is the following. first one. If you have an adjunction, then try to recognize it as a well-known one. And for the letter, write down Tensor-Hom-Cotensor. And second, think that once we have Tensor-Hom-Cotensor, we can use coherent calculus and other tools. Ever. In an example above, where we had Hom in lambda modules and Hom in abelian groups, similar as here, where we had twisted Hom and composition. We had, in this case, we had no idea who is left and who is right. I mean, who is tensor, who is Hom, who is cotensor. Okay. Also here, you see that twisted Hom is Hom and ren is cotensor. For profunctors, we had that for profunctors ren is Hom, but it matters which category we are working in. So always think about your category. Hint number 3. Think in what category do you work? So depending on the category, you will have different right, left scan extensions, weight limits, co-limits, Tensor-Hom-Cotensors, and so on. So taking all this together and being very careful will give you insane freedom. I will say that personally that this freedom allowed me to derive many results. And right now, in the last 5 minutes, I want to talk about the general summary of our lecture, of our few last lectures, and about all our course. So here is a summary. I wanted it to be as much both general and specific as possible. So I decided to make how I see at the current moment mathematics myself. I mean, this all mathematics, this homological algebra, category theory, and everything related to this. So on the top is the notion of Tensor-Hom-Cotensor situation. It gives us a junction, covariant and contravariant one. Even we don't need covariant one. It's enough to have contravariant one. If we had enough time, I would show you that Tensor-Hom-Cotensor can be defined symmetrically. We don't need to think who is acting on whom on the left, on the right. Just make every functor contravariant, and it will be huge advantage. But not about this. So once you define Tensor-Hom-Cotensor situations, from them you can define so-called functorial Tensor-Hom-Cotensor. What is it? It's that we can substitute all or wrap tensors in coends, cotensors in ends, and Homs in other Homs. So we can also implement diagrams where the targets for the diagrams for Tensor-Hom-Cotensor situation. For the economy of time, I decided not to give this, but this functorial THC, I mean, it looks very similar to weighted limit and co-limit situation. Very similar, and it's even from it you derive weighted limits and co-limits. That's the next step. Parallel to this, from Tensor-Hom-Cotensor, you can define a notion. It just define a notion. It's an example of V by tensor category. When your home is given by home profunctor, and here you go. It's an example of V by tensor category. From this thing, as we today saw, we derive that presheaves and copresheaves are always V by tensor. So they can be used as a coefficients for tensoring and cotensor. Okay, then from copresheaves being by tensor and weighted colimits, as I have shown above, when I was substituting C by C op to V, I obtained a Tensor-Hom-Cotensor for profunctors. Even just have when I have no idea about profunctors. So I'm just falling down in this diagram, going deeper and deeper. So Tensor-Hom-Cotensor, knowing quant calculus, give me functorial THC. Functorial THC, picking up correct friends, give me weighted limit colimit adjunction. Nothing, I would say, criminal. Just as a definition, it gives us immediately that thing. And they together give THC for profunctors. THC for profunctors, as you saw above, and weighted limits colimits give me both len and tren as Tensor-Hom-Cotensor. Parallel to this functorial Tensor-Hom-Cotensor, give me coends as Tensor-Hom-Cotensor situations too. So I can, from general Tensor-Hom-Cotensor situation, obtain one with integral signs and then obtain one for the correct definition of ends and coends. And they, as I wrote with a backward dashed arrow, blue one, they go or also give me THC. So they work on each other. Then from THC on profunctors, I decided to write the things that I couldn't cover in a course right now, since we do not have much time. I can derive so-called Isbell duality. Isbell duality, you can write yourself when you will use such a triangle of profunctors. So it's a triangle of profunctors where the intermediate category is trivial one. This duality gives you Auslander-Gruson-Jensen duality. Ekman-Hilton. It gives you which other duality? Post-spec duality. So global section and spectrum duality. And many, many more. In topology and algebra and representation theory and so on. Isbell duality, some people claim it to be a mother of dualities. Well, I'm not the one to claim it, but you can check yourself. And Isbell duality immediately you can get from this three profunctors. On the other side, when in a triangle of profunctors, you will pick up not the intermediate category to be trivial, but one of the other two, you will have so-called satellite triangles. One for covariant satellites, so this for covariant, and one is for contravariant satellites. Satellites are given in the book of Cartan-Eilenberg, and they serve as certain operations similar to right and left derived functors. And for half exact functors, satellites coincide with the derived functors. Later, then they were originally defined by classics. They were redefined in a way using Ken extensions by one mathematician called George Janelidze. And his definition of satellites incorporates classical ones and incorporates many, many more. So from his definition, you could derive homology functors, cohomology functors, and homotopy functors, and derive them together with natural transformation, which is called connecting homomorphism. So it all gives you for free also long exact sequences. And as you know, once you have long exact sequence in homology, cohomology, homotopy, you rule the whole that branch of math. But also by satellites, you can using satellites, you can define derived functors. Well, for this, to be very honest, I need also to write this arrow because derived functors using satellites can be obtained from zeros, left and right derived functors. And for them, we need left and right Ken extensions. So from this picture, you can say that once I know what is Tensor-Hom-Cotensor, and I have enough spare time, enough place where to write and think, and with what to write, I can derive most of the results in what people work. I'm not about some specific topics in groups and combinatorics and algebraic geometry because I don't know them. I can't talk about them. But everything what I have seen up to now falls in some way under this. The one thing that I haven't mentioned is so-called weighted. It's a derived notion from weighted limits and colimits. It's called defect theory. So defect is a left adjoint to Yoneda embedding. Yoneda embedding increases our realm from category to functor categories. Defect takes us back. It takes us from presheaves to objects. So if Yoneda gives from an object a presheaf that's represented by the object, defect moves us back. But for any presheaf, not for representable ones. So it pretty much gives us for our given presheaf, or it gives the best approximation by a representable one. So this is, I would say, a game between the dimensionability. So once we want to increase dimension, we apply an end. Once we want to decrease dimension, we apply defect. And there is an embedding. Sorry, there is an adjunction. That's also what I was working on the last year. And not only me, but also Professor Marcinkovsky and quite a big group of people. So that's the summary of what we were doing, what we were studying. As you see, we get only the things, even not all in the middle, but so many things are to the side. And I think during my lifetime, I will see many more things are going out to the sides and in the middle, filling the gaps, and so on and so forth. But right to now, Tensor-Hom-Cotensor, you can see everywhere. Also, another way how to recognize it, if you have an adjunction and the functors in the junctions that appear, they depend on a certain thing, as on some module, object, or whatever. Be sure that somewhere hidden is a third one, and you have Tensor-Hom-Cotensor. If they are just functors as pure, I don't know how to say it, independent on anything, they just exist, then, well, maybe I'm wrong. But if they depend on certain parameter, this parameter also can give you certain third part for your adjunction, and you will get THC. Well, right now I want to thank you everyone who was watching this course, who was participating, who was listening, who was reading, criticizing, emphasizing, opening my emails, reading them, replying to me, wanted to participate. I'm very thankful for everyone who participated. Also for Professor Marcinkovsky, who gave me such possibility to read such fantastic course. It was my dream, and thank you everyone. If I can answer any of your question, I will be very glad and hope I can help you somehow. If you want to ask me anything, we can ask this with a record or after I stop. Other questions while I'm recording? Okay, then there is a silence. I wish everything who is watching the record bye and see you soon. Right now I'm stopping the record.
Okay.